Young's double-slit experiment. Young's double-slit experiment is an experiment that shows wave interference, or the wave nature of light. So there are two theories out in science and how light behaves. It either behaves as a wave or it behaves as a particle. And this experiment shows that light can behave as a wave and act as a wave. Young's double-slit experiment will show an interference pattern on the screen, and this can be done through a process called diffraction. And diffraction occurs only for waves, and it is the bending of waves behind some sort of obstacle. And so what we would like to do, or what Young did, is created an obstacle or a barrier with two open slits. So we have some sort of barrier with two openings, and we have some sort of light source that is monochromatic. Now, monochromatic just means the light source is all the same color or has the same wavelength. Wavelength determines color. And so we have some color, perhaps it's blue, and we have this monochromatic wavelength heading towards the obstacle. When the wavelength hits the obstacle, the only pieces of wave that will go through are through the slits, the two slits. So we end up getting diffraction occurring at these two slits. And when this diffraction occurs, we have overlapping of the waves. And when we have this overlapping of the waves, we have interference. And on the screen opposite, we can see an interference pattern. And we get this interference pattern where we have the brightest light showing right in the center here. I'm going to use red actually. So right in the center, right along here, we have our brightest light like so. And then we have a dark band, and then a lighter band, and then a dark band, and then a lighter band. These are called fringes that appear on your opaque screen. Opaque screen means you can't really see through it, so you can put an image on the screen. And so these fringes here, so these are called fringes. So we have these fringes, and these fringes are numbered or have orders. So the very first fringe in the middle, along the midpoint where my red dashed line is, that has an order of 0. And that one, because we're seeing a bright light, we're having interference, we're having constructive interference. So at this brightest fringe, we have, we call an order of 0, and there's constructive interference there. Next to that, where we have a dark band, that would be here, it's also an order of 0, but here we have destructive interference. So here we have destructive interference, or we just see a dark band or the absence of light. And then away from that, we would then have an order of 1 for constructive, an order of 1 for destructive, order for 2, and it just keeps going. And we have the same thing on the other side. We have a destructive interference of 0, then we have an order of 1, 1, and then this one here would be 2. Now there is a formula we can use to try and determine all sorts of things with Young's double-slit experiment. So I'm going to redraw our two slits with our opposing screen, and we're going to label some of these things. We're going to have a distance between the slits and the screen. We're going to call that L. There is a midpoint right down the center, right in between really where the two slits are. There's going to be a distance from the center of the slits to the center of the other slit. That's D, or lowercase d. We will have our interference pattern, look something like this. Showing up on the screen when we shine monochromatic light from the left of the two slits. And what we know is L in blue is the distance from called my zero order, my first fringe, if you will, at the equilibrium. But what if I'm interested in my order of constructive interference at this point? Well, I'm going to draw a line from my midpoint to that fringe, and then there would be an angle that I could measure, and that would be an angle I'd be interested in. Maybe I would call that theta sub 1, because that's the angle to my first order of constructive interference. So we have a formula for constructive interference, and it looks like this. It's d sine theta is equal to m lambda. Now, as you can see in the picture, d is the distance from the center of the first slit to the center of the second slit. Theta is your angle from equilibrium to whichever fringe you're looking at. M is your order, and lambda is your wavelength. In this particular example, my order would be a value of 1. And this is only at the bright areas, or where constructive interference occurs. Okay, well, what about destructive interference? For destructive interference, we have a new formula, similar though. It's d sine theta is equal to m plus 1/2, and that quantity all multiplied by the wavelength of the monochromatic light. So it's very, very similar, but in this case, perhaps I'm looking at this spot here. This is where we have darkness. So this would be destructive interference. This also happens to be, let's see, this would be an order of 0, order of 0, order of 1. This is also an order of 1, but for destructive interference. So we would still plug in a value of 1 for the order, but you see that we would then add 1/2 to that. Okay, so let's go ahead and do an example. So we have our double slit, we have our opaque screen, we have our distance D here, we have a distance L between the two slits and the opaque screen, we have a midpoint here. And the question is, what is the distance between adjacent bright fringes? Again, what is the distance between adjacent bright fringes? So again, we're going to have our interference pattern showing the bright fringes. Does it on both sides? We know that we're going to have an order of 0, order of 1, order of 2. And what I'm interested in here is these angles. So I'm going to have an angle to this spot, and I'm also going to have an angle to that spot. My first angle here is theta 1. And my other angle, this angle right there, is going to be theta sub 2. And so if I can find theta 1 and I can find theta 2, I can probably find everything else I need. Now, what we were finding, though, is the distance between adjacent bright fringes. So really what I'm looking for is this distance right here. I'll call that, say, x1. Or better yet, I could also find this distance here, what I would call x2. So we have an x2 distance, and we also have an x1 distance. If I could subtract, say, x2 minus x1, I could find that distance between the fringes. That'll give me my answer. Okay, so I've drawn my picture. Let's write out our given. So for our given, we do have a distance between the two slits, and it's 0.1 millimeter. And of course, that is going to be 1 times 10 to the minus 4 meters. Our L is going to be 1.20 meters, and my wavelength is going to be 500 nanometers. Now, nano is a prefix for times 10 to the minus 9 meters. Okay. I want to go ahead, I want to insert a few zeros for my distance between the two slits, just in case I want to round my answer to two significant figures. So let's do that. Okay. Alright, so the formula we're going to use, because we're talking about bright fringes, is the formula for constructive interference. And so that's d sine theta 1 is equal to m lambda, or sine theta sub 1 is equal to m lambda over d. If we plug in the numbers, the order is the order of 1. The wavelength is 500 times 10 to the minus 9 meters, and the distance is that 1.00 times 10 to the minus 4. I get an answer of, let's scroll this up here, I get an answer of 5.00 times 10 to the minus 3. Now what this means is theta sub 1 is a very, very small number. And when theta sub 1 is a small angle, then my theta sub 1 is almost exactly the same thing as sine theta sub 1. So in this particular problem, I'm going to replace sine theta sub 1 with just theta sub 1. And so when we look back at the picture, if I want to use trig, we can see that my x1, I'm going to show here in green, over my L value is going to be equal to sine theta sub 1. So when I write this out, I will have my x1 over the L is equal to sine theta 1, which is approximately theta sub 1. Rewriting that then, I'm going to have theta 1 multiplied by L is x sub 1. And I really ultimately want to find x sub 1, so I can subtract it from x sub 2 and get my answer. And so plugging in the numbers for theta sub 1, we'll put 5 times 10 to the minus 3. And we're going to multiply that by L, which is 1.20. And we get an answer of 6.00 millimeters. Now, for the second order, then we're going to have x sub 2 over L is equal to theta 2. So, in other words, I will have theta sub 2L is equal to x sub 2. I'm using the formula above. Now we have a second order, so we're going to have 2 lambda d times L, and that ends up being 2 times the above number, or 12.0 millimeters. That's a point there. So when we subtract those two values, we get an answer. If we take the x2 minus x1, we get an answer of 6.0 millimeters. And here's your practice, problems 3 and 5 on page 692. Good luck.